The objective of this video is to develop the winding layout design methodology for single-layer integral slot windings. So far in this class, we've been talking about windings largely in terms of analysis. We've figured out ways to calculate the winding factors for a winding. We've developed design expressions for determining the number of conductors we require in a slot when we're given the winding layout. But this video launches us into a unit on the actual design of windings. That is, how do we decide which phases coil sides belong in which slots of our stator? And we're going to develop that in this video for single layer windings. Single layer windings means that you have one coil side in a slot. And further, this is going to be specifically applied to integral slot windings. And integral slot windings means that your number of slots per pole per phase is an integer. In a later video, we'll be talking about scenarios where your numbers of slots per pole per phase is a fraction or doesn't have to be an integer value. But that is a more advanced concept. And we want to start with integral slot windings because we can understand them readily by drawing cross sections of our motor and mapping that to our star of slots. I want to start by talking about our expectations for our winding, what we're looking for our winding to do. And as we've developed so far in this class, we have some fairly specific expectations, both in terms of the magnetic field behavior of our winding and the electric behavior, the voltage behavior of our winding. And so we're going to construct this little chart here showing our expectations for both the magnetic field behavior in terms of the circumferential current density, the equivalent circumferential current density of our winding, and our expectation for the phase voltage of our winding. And these are our two categories of magnetic and electric requirements. And as we've developed so far in this course, we've talked about windings as being able to create an equivalent circumferential current density on the inner bore of our stator. And we use that circumferential current density to derive our motor sizing expressions. So we defined an electric loading quantity that was a fundamental aspect of our machine. Our circumferential current density created that electric loading, and our circumferential current density is created by the windings of our machine, by the coil sides in our slots. And so we've talked about how the circumferential current density can be expressed as a Fourier series. And those Fourier series components we derive from the current linkage when we study a winding. And all of our expectations on this in terms of creating torque were on the fundamental quantity. That is the harmonic 1, V equals 1. We expected our circumferential current density to have the following form for our fundamental harmonic. And these expressions that I've written down here show how we want our circumferential current density to distribute itself on the inner bore of our stator. And remember, this is just the harmonic representation of it. In most cases, we don't actually have conductors distributed in a sinusoidal manner on the inner bore of our stator. So all of these terms that I've just written out are actually just a fundamental component, or where V is equal to 1. And so we could show an index of 1 on each of these terms if we wanted to, but we'll leave that off just for brevity. And this is again a review. If this is a surprise to you or confusing to you, I encourage you to go back and look at the videos related to electric loading and our equivalent circumferential current density and rotating current densities. And so we use these three current densities to create a rotating circumferential current density in our stator, which we could relate to the linear current density and get electric loading expressions. So that was our expectation for the fields that we produce in terms of the equivalent current density. Now we also have expectations for the terminal voltage of our machine. So that is where we connect our motor to a motor drive or to the power grid. And those expectations are that we have sinusoidal voltages that are spaced out in time by 2 pi by 3. So these are our expectations. This is what we are trying to create. In reality, we have more harmonic content in a practical winding system, but this is our goal. And so now let's sketch what this meant on how we studied this on both sides of the page. So on the left side, we'll start with current density. And we had drawn these three expressions as sinusoidally distributed currents. And so I'm sketching a rotor, and then I'll show these angles that we had labeled in a previous video. For phase U, we had said that we had a maximum number of conductors out here at plus and minus 90 degrees, and then a minimal number of equivalent conductors very close to the phase axis, which we'd label as alpha U. So we had assumed when we originally sketched this, we had drawn it kind of like this, where we were indicating a sinusoidal varying number of conductors. Now in this case, I'm only showing conductors where we had them peaking at plus and minus 90 degrees. And so we can draw the same thing for phase V and W. And so this spacing and these lines all match up to these angles that we've indicated up here. Alpha U was 0, alpha V is negative 2 pi by 3, or 2 pi by 3, and alpha W is 4 pi by 3. And as I've sketched this right now, this corresponds to a motor with P equals 1 pole pair. Now, we studied our phase voltage by constructing the star of slots and then placing individual coils into phases. And we then constructed a phasor diagram that we were trying to realize from our star of slots. And our desired phasor diagram is the phasor representation of these three voltage waveforms that we've indicated above. And so we construct our voltage phasor for an individual phase as being the sum of a series of coils. And this voltage phasor is the voltage representation between the neutral point of our winding and the terminal of each of the phase windings. Okay, so we did this for a one-pole pair motor. Now to illustrate this a little bit further, let's repeat it for a two-pole pair motor. And so in the two-pole pair motor, we have the same pattern as we had up here. It's just that it repeats itself twice as we walk around as we take one revolution around our stator. And I could draw the conductor cross sections. I'm not going to do that because that would take up too much space to be cluttered, but I think you get the idea. And the spacing here now is going to be pi by 3. And what we expect from our electric characteristics, our back EMF, is exactly what we had for the one-pole pair motor. So our expectations in terms of current linkage change. We want the current linkage to repeat itself more times on the inner bore of our stator, but our expectations from our voltage in time stay the same. We have a certain electric frequency, and we expect that our phases are distributed within that electric frequency by 2 pi by 3 radians. But again, these are electric radians. So if we were to draw an equivalent two-pole representation of this, we would end up with this up here. And we talked about this in a previous video. The point of this is that I want to highlight what we expect our winding to do, and then use this to motivate how we design our winding. Now, we have a few more things to talk about before we get there. We're going to assume that our connections to the coils are on the top of our page as we draw it, and then we're going to use a passive or motor sign convention. So let's draw what this looks like in 3D space. Say that we have a salient pole rotor that's rotating counterclockwise, and there's a coil that is surrounding it. And so a coil consists of two coil sides. So I've drawn coil sides here that are in the slot. These are going down into the page, into the slot of our machine. And of course the rotor is in the center, and it's spinning counterclockwise like we always do. And these coils are connected somehow. The coil sides are connected. They have an end connection that connects them on the top and the bottom. And then they're somehow connected to the outside world. And what I'm saying is that connection is going to appear on the top of the page. So this end connection, the coil is wrapped around some number of times here, right? ZQ number of times. And then there's an end connection that comes out, and that's what connects to the outside world. Now, as we've been drawing our current directions, so I put an X on the top because when we look at it from the top of our page, we just see that X. But then this blue arrow is showing it's going down, and it travels up to the other coil side, and then it comes back up out of the slot, which means we see a dot here in the center. And if we're using the passive sign convention, so if this is our current direction, I, if we're using the passive sign convention, that means that we apply a positive voltage, or we take voltage as positive where the current enters. So we would call this the positive terminal for our coil. And negative is where the current leaves. So this is the negative terminal of our coil. So this can be a bit confusing because we're now saying that we're denoting the positive connection as the current going down into the page. But remember when we introduced our sign convention for current in the slot of our motor and in the air gap, we said that positive current is in the Z direction. It comes out of the page. So you have to keep this straight. This diagram is something that I expect you'll want to come back to from time to time. This is an important thing that's going to make the rest of the video make sense. So please be sure that you follow what I'm saying here. So that is, we have a difference in sign convention between what we might think of as the connections to our coil. So I'm calling this connection U1 plus and this connection U1 minus. That's because this is coil 1 of phase U. So we have 1 because it's coil 1 of phase U, and U because it's phase U. And so we call the positive terminal where current enters and then flows down. And the negative terminal is where current exits, which means it has to come up out of the page and this way. Okay, and I want you to be very careful to note that this is a point of potential confusion, danger, monsters ahead. Be careful because this might tempt you to swap the direction of your current density vector, but we take current density as being positive in the plus z hat direction, and the z hat direction is this way. Okay, so now that we've done this, we can make a comment. We can relate this figure here to our diagram up here. And what we're going to do is we're going to notice that, well, anytime we see an X, we say that that's a U plus conductor. And anytime we see a dot, that's a U minus conductor. So we're going to add those labels on our figure above. So these are U minus conductors up here. These are U plus conductors down here. These are W plus conductors, W minus conductors. All right, and this is important information for when we go to sketch our winding schematic. So given that, what we notice is that if we start at the first portion of our coil side for phase U right here, and then we walk around our motor in this direction, we have a sequence of phase bands, a sequence of zones. So this first zone right here is our U plus zone. Then we get to W minus, then V plus, U minus, W plus, V minus. And so what we're drawing down here is that sequence going from U plus, W minus, V plus, U minus, as we go around alpha, U plus, W minus, V plus, U minus, W plus, V minus, as we go around our air gap in the counterclockwise direction. And the sequence repeats itself. So for the two-pole motor, when we get out here, we're at 2 pi radians. But if we're talking about the four-pole motor, which we've sketched up here, suddenly we get past the V minus zone and we're back to a U plus zone, and so on and so forth. So making this observation that we can view our winding as having conductors in these zones as we go across the periphery of our air gap, we can propose a simple approach to laying out a winding. And that is that we will partition our stator slots into phase zones. And I'm going to introduce this by considering an example of designing a 4-pole 12-slot motor winding. And so I've sketched this with a 4-pole permanent magnet rotor just to help make it a little bit more obvious what we're doing, although we're talking about the stator. So I've then drawn circles for each of the slots. So we're going to fill that circle with a cross or a dot to indicate the direction of a coil side, and then we'll place a label of a U or a V or a W to indicate which phase the coil side is assigned to. And the first thing I want to comment on is that we're going to divide this into poles. And so you can see I'm labeling this angle out here, which is the pole span of our design. So a pole span is 180 degrees electrical, or it is pi by p radians. So it's the angle that a pole of our winding takes up. And we can also talk about a pole span as a linear length, as our book does. It defines this variable tau p, which is equal to our pole span angle times the radius. And so a pole span is always going to be pi electrical radians. It's always 180 degrees electrical when we talk about the equivalent two-pole motor. And then within a pole span, we're going to divide up our stator porphyria into phase zones. And so all of this I'm developing now, I'm giving you examples in terms of this being a three-phase motor because that's the most common case, but I'm going to be developing our design expressions in terms of a general motor which may have m phases. So for a three-phase motor, m is equal to 3. And these phase zones are going to be dividing up our pole into our three phases for a three-phase motor. So therefore the phase zone has a span of pi over m electric radians. And our book talks about a phase zone as a linear length, which is just going to be the mechanical angle times our air gap radius again. Or we can express it in terms of our pole span. Our linear pole span is our pole span divided by our number of phases. So we've got three phases, which means that each of these phase zones is going to be 60 degrees electrical, or, because this is a four-pole motor, it's going to be 30 degrees mechanical. And so we'll divide this up all along the periphery of our surface. And within a certain zone, we expect to have some number of slots. And this is going to be the value of our slots per pole per phase. And remember that we had said that the condition of this winding approach that we're developing now is that we have an integral slot machine, which we said meant that little q is an integer. So therefore, we have an integer number of slots within a phase in order to be able to use this winding layout technique. And this is actually how you classify motors. So if q is an integer, it's called an integral slot motor. And that is when this layout approach works. If q is a fraction, we say that we have a fractional slot winding. And in that case, you need to use a more advanced layout approach, which we'll talk about later. So what we're going to do to lay this winding out is we're going to go back to our observation up here that what we want is to have coils arranged around the periphery of our rotor in this sequence of U plus, W minus, V plus, U minus, W plus, V minus. And so we indicated that sequence out down here, and we'll assign each of those terms to each of the phase zones. So we're going to start here at alpha equals 0 and say that we have U plus, which, remember how we've indicated our sign convention up here, is going to be an X. It's going to be current into the page. And then next in our sequence, we have W minus. So I'm looking at this sequence right here. We did U plus already. Now we're going to do W minus. So that's current into the page. And after that, we've got V plus, and then U minus, and so what we notice when we assign this is that we have our sequence play out once over here, and then starting here at slot 7, our sequence repeats itself. And this is because it's a 4-pole motor. So we have one period of our sequence over the first pair of poles, and then we have the second period of our sequence over the next pair of poles. And so if this was a 6-pole motor, we'd have 3 repetitions. If it was an 8-pole motor, we'd have 4 repetitions. So it repeats based on the value of p. If p is equal to 1, it exists once. If p is equal to 2, it exists twice. There's a repetition of it. And so that is the simple layout approach, is that we divide the periphery of our stator surface into these phase zones U plus, W minus, V plus, U minus, so on and so forth, all of which have a mechanical angle of pi by pm radians, all of which have this mechanical angle. And then we just assign our coil sides. And at this point, we've talked about how these coil side directions map to an actual current, or an actual coil, up here. So as soon as we've assigned our coil sides, we know how to construct our winding layout schematic based on how we've set up the definition of this coil. So one more thing to point out about this is that we can talk about the span of each coil. So remember, a coil consists of two coil sides, and the shortest path that we can get for a coil span is to connect this coil right here to this coil, which means that the coil spans 1, 2, 3 slots. And we can then repeat this for phase W. It spans 1, 2, 3 slots, and phase V. And so what we notice with a single layer winding, at least using this winding layout approach, is that we're always going to have a coil span which is equal to the number of slots that fit within a pole. So we say that the span of each coil is a value of y, and the span of a full pitch coil is a value of yq. And for this winding layout technique that we've just developed, y is always equal to yq, which means that our winding is always going to have coils that are full pitch. And the pitch length, or the span of that coil, is going to be our number of slots divided by our number of poles. And the number of poles is 2 times p. So later we'll talk about what it means to have a short pitch coil and why you would do that and how you would do that. But in this video, we're going to focus on these being full pitch coils for this simple layout approach. So far we've considered the layout approach from the current linkage perspective, from the magnetic field perspective, from where we want to put coils in slots in order to create the desired current linkage. So that was the left-hand side of this table that we constructed up here. Now let's talk about it from the phase voltage perspective, from how we construct our voltage phasors to meet our requirements for what we want each of the terminal voltages to be. And it turns out that we can design our winding from this perspective as well, and it's a little bit simpler. But let's start by just constructing what our star of slots will look like for this stator that we've laid out. And so our spacing between individual slots is going to be 2 pi divided by q. But since this is a 4-pole machine, that means that our phasor spacing, our spacing between slot phasors, is going to be 60 degrees. And so again, I'm just drawing the phasors for this slot right here, this slot right here, slot 3 over here, and so on and so forth. So you can see that after I get to slot 6, I've completed 360 degrees electrical, and then moving on to slot 7 through 12, I go around the loop again. And then if I bring over our coil side assignment, if I notice, well, slot 1 is in phase U plus, slot 2 is the W minus connection, slot 3 is a V plus connection. I can label that as well. And again, I'm just looking up here, so I notice that slot 2 belongs to W minus, so sure enough, I've labeled W minus. We can audit slot 12 is V minus, and that matches up here as well. So I've just brought these labels down over here. And then I can redraw this for what our individual phase voltage phasors look like. So for phase U, I've got a positive 1 phasor, a negative 4 phasor, a positive 7 phasor, and a negative 10 phasor. And then for phase V, I've got a positive 3 phasor, a negative 6 phasor, a positive 9 phasor, and a negative 12 phasor. And finally for phase W, I've got a positive 5 and a positive 11 phasor, a negative 2, and a negative 8 phasor. And so you can see that from the voltage perspective, we've accomplished what we wanted. We have gotten our 3-phase voltages separated by 120 degrees. We've created this circumstance here. And finally, we can use this information to construct our winding schematic. And so we can see from our winding layout that we've got coil side 1 attached to U plus, coil side 4 attached to U minus, and that forms one coil, which must presumably be connected in series to coil side 7, which is connected to coil side 10. And noting the X's and the dots, we can match that up to this diagram here to say that, well, U plus attaches to our X, U minus attaches to the dot, and we can see how this would be connected into a winding schematic. So I'm going to use the information contained in this diagram, to construct the schematic diagram that we've been drawing in our exercises. So we'll start with coil side 1. It's connected to U plus. So we'll assume that that's actually the connection of our coil coming in. And we notice that we've connected coil side 1 over to coil side 4. So that forms a coil. All of our coils have a pitch of y equals q divided by 2p. So in this case, y equals 12 divided by 4 is equal to 3 slots. So that means we can say that coil 1 is going to connect to coil side 4 to form a coil. And what I've drawn right here at this point is this over here. And we can place terminal connections on it then. So this right here is this right here with these connections. And next we notice that we have the second coil out here from slot 7 to slot 10. And so the question is how to connect these. Well, if we say that slot 1 starts our phase terminal, our current's flowing down, down, over, up, and it repeats this path however many turns we put on, but eventually it's going to come out of this terminal, and then we want it to go down into slot 7, so we'll add an N connection over here, and now our current can come down through here, over, up, and out over here, so this is the negative of our phase connection. So we've just taken this diagram with this convention and we've turned it into this winding schematic. We've got all of our coils connected so that we have a U plus and a U minus as our connections for our phase winding. And of course we have several coil sides left unconnected, and those are for coil sides V and W. So we can redraw this phase winding for phases V and W by just shifting the phase U winding diagram over one slot or two slots. And you can see that pretty easily. There's one slot separation would be a phase difference of 60 degrees electrically. And so in our case, we have to shift over two slots to get the 120 degree separation, which means that we'd have phase V connecting coil 3 to coil 6, and then over here. And if you check that up here, you can see indeed that's what we have. Here's 3 to 6, 9 to 12. But we are not going to draw that on here because we're just going to show the phase U connections. Okay, great. So now we've got a layout for our winding, and presumably we've wound our stator. Now the question is, how do we connect it to a power supply? How do we connect it to the grid or to a motor drive? And for a three-phase motor, there's two connection styles, a star or Y connection and a delta connection. And so I'm drawing this as a set of inductors, symbols, that are connected to a neutral point. Each inductor symbol is our winding, is our phase winding. So this entire circuit here is distilled down now to one inductor symbol, which represents all these coils connected together to complete this path. That means that this terminal right here in the top, this is U plus and this is U minus, and we'd expect to have a current source here, which is our motor drive or our power grid, of value IU. So this IU is mapped way back here to this up here. This is to get our circumferential current density. So we have an IU right here, which is what we flow into the terminal of our motor. And that was also what was indicated right here, right? Which takes this path right here which we're now finally showing in a schematic connection right here. And then we have phases V and W as well. So that's one type of connection. That's typically what we'll be talking about in this class. You can also connect this as a delta connection. This is particularly popular for induction motors, which looks like this. So now your coils, your phase windings are connected in this triangular configuration. But most of the time, we'll be talking about this in this class. Okay, so we've kind of meandered around here by talking about how we can lay our winding out with different, progressively more refined. So we start out just by observing a sequence of conductors that we want around our rotor. We've then defined some nomenclature and some sign conventions for how we indicate our voltage and our connections to our coils. We formalized this by talking about an approach to dividing our stator periphery into phase zones, where each slot in that phase zone is assigned to a certain phase. And then we noticed that we can equivalently represent this as a star of slots, where we repeat the star of slots pattern the same number of times as we have pole pairs, the same value as we have for P, which is actually gives us a unique mapping between these two surfaces, between these two visualization tools. So the star of slots and this layout of dividing our stator periphery into different phase zones have the exact same information. They tell us which coil sides are assigned to which phase. So in this diagram up here, it's literally the coil sides that we see, whereas in this diagram down here, it's actually the phasors for each slot phaser that we see. And then we talked about how we can go from that to constructing a winding schematic, and then how we can connect it to a drive. So what I want to do at the end here is formalize the design procedure. And what I propose as a design procedure, what the standard procedure is for these single layer integral slot windings, is to use our phasor star of slots diagram to assign coil slot phasors to phases. We do this knowing that it's equivalent to this approach up here because it's simpler. We can quickly construct this star of slots by knowing by some simple calculations for what the spacing should be between each of our slot phasors. And then if we have a lot of slots, we just go around this path multiple times. And so we can take a winding that has a very large number of slots and much more quickly draw this than we can draw this, which means that our star of slots is a more useful and practical design tool for assigning our coil sides to slots. So we're going to write these rules out for how to lay out a winding, and we're going to write them out for the star of slots. So our first design step is that we sketch our star of slots for the fundamental harmonic, for V equals 1. And then on our star of slots, we label phase bands of pi by m radians. So what we're saying is that we're going to take this star of slots and we're going to say that we're going to have pi by m radians where any phasors within that region are assigned to a certain phase. Just like we did on the periphery up here, now we're doing it on our star of slots, but the star of slots is always drawn at the electrical frequency, so it's always pi by m radians. And then finally, we convert the assigned coil sides to a winding schematic. And we do that by going back to what we set up here. By knowing that anything that is assigned to U plus is where current enters, and anything that's assigned to U minus is where current has to leave. So just as an example, let's depict this for a P equals 1, Q equals 12 winding. Up until now, we've been talking about a P equals 2, Q equals 12 winding. Now we're talking about the P equals 1 version of that. And so we're going to first draw our star of slots, because that is step 1. And to do that, we'll notice that our spacing between our slots is going to, again, be 2 pi divided by 12. And this time, our slot phasor spacing is also going to be pi over 6. And notice that right away we can talk about how many phasors we have within one of these phase bands by looking at Q, where Q is equal to, little q is equal to big Q divided by 2pm, like we previously noted. And in this case, that value is 2. So that means we expect to have 2 slot phasors within each phase zone. And drawing our phase zones on here, we can now see how our coil sides are assigned to the phases. So in this case, coil sides 1 and 12 are on the U plus connection. That means current is flowing into these coil sides, whereas coil side 6 and coil side 7 are in the U minus assignment, which means current is flowing out of them. And so we could again construct our winding layout schematic from this information. And so I want to point out again when this approach works and when it doesn't. And so this approach works for any integer slot single layer winding. And it will also work for integer or fractional Q double layer windings. However, we're going to talk more specifically about double layer windings in a later video because there are some specific nuances there that you can use to speed up your winding layout. Okay, so in summary, this video has developed the single layer integral slot winding layout approach. We've started with observations about what we desire from our magnetic field perspective and from our phase voltage perspective, from our electric circuit perspective. And we've used these observations along with a definition of how we consider our coils to be connected to derive a simple layout approach, which is based upon phase zones placed in the periphery of our stator, placed on the surface of our slots. And we made some observations about how this was equivalent to using the star of slots to make these same assignments, and then how we can extract information from the star of slots, or our periphery diagram, to construct a winding schematic. Then discussing how this can connect to a power source, what this actually means. We've laid out our winding, how do we actually use it? To finally deriving, or summarizing rather, a formal set of steps for laying out our winding. And so what I put in this highlighted box right now is what I want you to remember. This is a fundamental building block for our course. Please make sure you understand this. Please come talk to me if you have any questions. And finally, we gave an example of doing this for a 12-slot 2-pole motor.